Okay, here we go. All right, so I need to just define some terms first. These terms are not defined in your packet, but these terms you will probably have read multiple times. Actually, in the packet you're reading 20 to 25. It wasn't in there as much, but I need to just tell you what they are, and then we're going to be able to identify them in a specific reaction or a specific step, an elementary step. So you know that most of the time reactions are going to happen in steps. You're going to have, and this is going to resemble Hess's law. You're going to have a reaction that you have A and B react and they form C. Well, then C is going to react with D and it's going to form E, or it's going to make C and D, sorry. And then C and D react to form E and F, and then E and F will then react to form Z. Well, some things are going to continue with us all the way through to the end of the reaction. Some things are going to get immediately made, immediately used. So they're going to be individual steps, and so I need to be able to identify and talk about what these things are. So intermediates. Well, what is something that's an intermediate just in general for you guys? So like if you have to go tell Krista about like somebody else, I'm going to tell an intermediate. I'm going to tell Sarah, like, oh my gosh, did you see her in that tight dress? Do you see her? She's going to go tell Tara. She's going to go tell somebody else for me. She's going to be my intermediate. Okay. So we're going to talk about things that come into existence and then disappear. So whenever you're giving like in a definition, you always say species. We're not talking about biology. We're just talking about chemical species. Species that is not they're not a original reactant. Okay, so it's not an original reactant or an original product, but it's going to be that first product that's formed. This is a final product. I kind of have to specify there. That's going to be formed early and then consumed in the next step. So in my example up here, two intermediates are what? I'm going to go C and D for my first one, for my first identification, because they're the first things that are formed, and then they are immediately used or used up in the next step. So they're going to be reactants in the next step. You would also be identifying E and F as intermediates because they are now produced and then immediately consumed or used up in the next step. So those are some intermediates if you want a specific example there. Then we've got elementary step, and we basically defined this already, but it's going to be just one basic, I would say elementary is like your basic knowledge of school, so one basic step. And most of the time we cannot look at the stoichiometry. We cannot look at the balance part, the BCE, and go, yep, I can make a rate law from that. That is illegal. But right now, when you're only considering one itty-bitty tiny step of the full reaction mechanism, you are allowed to do that. So if I give you that first reaction, A plus B yields C plus D, what are the reactants? A and B. So I would officially be legal in saying rate of elementary step 1 up here is equal to K, A to the molecularity of that first step is 1 for coefficient is 1 for A, and it's 1 for B. Normally, you're not even supposed to look at the balanced chemical equation when you're determining rate laws. But that's because most of the time we're looking at the overall picture, not the baby steps. Does that make sense? Why I'm allowed to do this at this point? I'm allowed to take the BCE and turn the coefficients into exponents. Why is this different than what we were doing 2 days ago? Right, this is not the final BC. This what I'm talking about. Just that first step is just one part, and that is a bimolecular reaction because it only has 2 reactants, and that does play a role in how fast it can react. That first step, and that for overall BCEs, for the overall reaction, you're not allowed to take the coefficients and make them into exponents. That part is the part that's a no-no. All right, the rate determining step is another definition you're kind of familiar with already. It is the step, the elementary step that is the slowest. So another name for this is the slow step. A lot of times this rate determining step is identified by writing in parentheses next to the elementary step, parentheses slow. Just so you know it's the slow step. And this right here, this step is controlling the overall rate, so it's the most important. So when it's determining the overall rate, it literally determines the rate law. So in my above reaction, go down just far enough for me to write up there. In my overall reaction, if I had written next to the second elementary step, slow, you would be seeing that as the slow step, right? So from that slow step, what is the rate law? Equals what? The molecularity of that elementary step, but what is it then? Rate equals K to the first, because there's a 1 there, and D to the 1, because there's a 1 there. All right, and that's because it's recognized as a slow step, and the molecularity of that elementary step is allowed to be transferred as those coefficients to exponents for the rate determining step. And then here again we have molecularity. It is supposed to be indicating the number of molecules colliding, but you can also talk about it represents the stoichiometry. Stoichiometry is kind of it's like the produce kingdom, just kind of throw everything in there because it's referring to coefficients, VCEs, relative natures of reactants. So stoichiometry of the elementary step. So I put catalyst way far away from intermediate because I don't want you to mix those two up. So intermediates are what and then what? They are produced and then immediately consumed as a reactant, right? Catalysts are present at the very, very beginning. Okay, so they're pretty much opposite. They're present as a reactant in a very, very, very early step. They're going to get kind of, they kind of disappear for a while, but then they again show up in the final products. So they are reacting in an early step and a product in a later step. So in the end, you will see them, as a catalyst, as a reactant, and then you'll see it again as a product. You in the second, I'll teach you how to cancel these things, but it's like Hess off. It's on the left and the right. You can cancel it. So you'll be canceling them, so it looks like it disappears. But does a catalyst get used up? No, it does not get used up. So it looks like it disappears, but it doesn't. It's just, is it relevant to the rate law itself? No, it's not technically a reactant. So you cannot put a catalyst in a rate law generally. Sometimes you will see it that way, like for zero order rates, because the catalyst actually determines the rate. It's just commonly not written that way. So not technically a reactant, so not in rate law. What else do we say? Not consumed or used up. And generally, the words that you should be associating with catalyst are provides a alternate pathway, thank you, alternate pathway for reaction that has a lower activation energy. All right, so terminology savvy we are now, yeah? Okay, let's practice. Okay, this soon, oh no, we're not using your notes yet. Okay, oopsies. Okay, so these are the two criteria that you kind of read about. These are the two criteria that must be met for a reaction mechanism. And let me show you what a mechanism looks like before you write. So a mechanism looks like a step and another step, and it could be 4 steps, but it's just a bunch of elementary steps lined up together. That's what I mean by mechanism. Okay, so a mechanism is true for the overall VCE that's given. Usually it says overall reaction VCE. If the sum of all the elementary steps equal the overall reaction. This is where you sum up elementary steps by canceling. Canceling is 2 L's, right? No, it doesn't. Canceling reactants and products on both sides. It does.
Canceling.
Yes, it does, right? By canceling, I'm just going to say it. I don't have to spell it when I say it. Reactants on both sides of the reaction arrow. As you cancel, like it says, like Hess's law. As you cancel and you bring all the reactants down and all the products down that remain, you compare your overall balance chemical equation to what you have produced in that cancellation. If they're the same, we're good on 1 out of 2 criteria that must be met for a possible reaction mechanism to be true. So we're concerned about like possible reaction mechanisms being true for a rate law overall, because intermediates are sometimes really hard to isolate, to actually catch and see, yep, that's the intermediate. So a lot of times scientists kind of use their best judgment on what each baby step of reaction is. So if they're making the best judgment on what each of the baby steps are, we may or may not be totally 100% sure on what the intermediates are for each of the individual steps. So we can propose things and say, yes, this is a possibility. If it meets these two criteria, we go with it. We're like, yeah, this is a possibility. I don't know it to be 100% true, but it's a possibility. Okay, second one is rate law written from coefficients of rate determining step. So rate determining step molecularity, match rate law coefficients. That's basically what that means. I'm sorry, not coefficients, exponents. Rate determining step molecularity, which are the coefficients, match the rate law exponents. That's the shortest and sweetest I can make that one. So like we were doing earlier, if I identify a step as slow, I look at its own coefficients. So the reactants, do I look at the products? No, because rates have nothing to do with products at all. Rates only deal with reactants. I look at the reactants, look at their coefficients, pull them up, make them as exponents for the rate determining, for the rate law. And we're going to practice with this. So your slow is your weakest link is generally the best way to describe it as well, because if you have 15 steps and you got one that's really slow, it's overall slowing down the entire reaction. So that's why it's called the rate determining step. It can't be slower than your slowest elementary step. The last little part here I think is fairly common sense. It's the prefixes that relate to number of molecules colliding. So if you're dealing with a reaction that only has one reactant, it is called unimolecular. One, unimolecular. And that one's kind of like, duh, we got that. What kind of reaction would have, or an elementary step, what kind of reaction would have one reactant? Decompositions, thank you. Decompositions would generally have one reactant. That one is kind of common. You have to have a little energy to help that thing decompose because it's it's stable enough to exist. So you might need a little heat behind it to actually force it to occur. So if it doesn't naturally decompose at a very fast rate, it might have a high activation energy to be able to decompose. So sometimes this is related to having a high activation energy because you have to heat it up usually to allow for something to decompose, like potassium chlorate. What's potassium chlorate? Thank you. How does it decompose? Say again. Thank you. You can balance that. I'm just making sure we remember that. Okay. So bimolecular means two things collide. That is the most common by far. But what can limit its ability to make an effective collision still when two things collide? Right. So generally, the thing that's going to be kind of causing that not to be an effective collision is the orientation issue. And then termolecular just means three things colliding. Can you imagine coordinating three orientations in the correct, or three things colliding in the correct orientation? Not the easiest thing to do, especially if the atoms don't have brains. So they're not going to be able to, like, okay, you move to the left 90 degrees and try to collide in the correct manner. So that one's fairly rare, but it can occur. All right, cool. Is this on your paper? Where does it say reaction mechanisms? Then you've got this. If you can fit it on there, fit it. If not, you write what you need to. So our job is to consider this overall BC that's given to us at the top. We are given the rate law itself, and based on the two criteria, does it match? Are both criteria met so that we can actually say, yes, this is a possible mechanism, two-step mechanism for that reaction up there. So first step is to add up your elementary steps. So add them up like Hess's law. What do you notice can be canceled from left and right? Nitrogen dioxide, and NO3, which is nitrogen trioxide, and nitrogen trioxide. Anything else? No. So what pulls down? And CO, okay. Oops, sorry, CO. So nitrogen monoxide and carbon dioxide. All right, so does this overall addition of our elementary steps match our overall BC? Yes, okay, check. one criteria has been met. Based on our knowledge that this right here, this rate, represents the slowest step of the reaction, can you identify which of these steps is the slowest step? Which one? First one, because of what? Okay, you said NO2 too. You did not use my words. What are my words? Of the matches the. So the molecularity of the first elementary step matches the exponent, okay, I go with that, exponent of the rate law. That is the one sentence explanation you should probably be writing if you're trying to justify why you have identified something to be as the slow step. So the molecularity, that word says, I hate writing out molecularity of the of the first elementary step matches the exponents of the rate law. And you can see I've not actually canceled, like said, okay, this is totally gone, this NO2 is not gone. I have just utilized my knowledge of intermediates and catalysts in order to make my final addition of the elementary steps. This still exists here, and I can see that I have, when I combine it, it's 2 NO2, and that 2 is translated as an exponent in the rate law. So therefore, you would say this is the slow step right here. Now, you know what intermediates are and you know what catalysts are. Which one is an intermediate from our steps, our mechanisms? Which one's an intermediate? Okay, so NO3 is an intermediate because it appears and then disappears, or is consumed. Which one's a catalyst? Right, NO2 is a catalyst. It happens to be a catalyst and a reactant in this case because it is showing up in the actual rate law. There's another, in this example, there's another chemical in action helping it to decompose. This specific example is your catalytic converter. Remember I drew my picture? We had our poisonous nitrogen dioxide stuff being converted to nitrogen monoxide, nitrogen trioxide. It gets consumed right here, reacting with hazardous carbon monoxide to produce not so bad, to the health, but not so much the environment either, to the carbon monoxide to the carbon dioxide, and then the carbon monoxide remains because apparently nitrogen dioxide is way worse than nitrogen monoxide. So there's a catalyst behind this that we don't see. My example that I used earlier for that catalyst was platinum for your catalytic converter. You need to know generally, not rare metals, what word is that? Precious metals. I guess precious metals are used as catalysts a lot of times. So platinum is a good example. Lead is a good example. It's not really that precious though. Gold is sometimes an example of a catalyst. Surface, they're metal surfaces. Gold, platinum, and lead. Okay, so I decided how many steps in my mechanism. 2 steps, 2 elementary steps. 1, 2, 2 rows, right? That makes a totally different reaction coordinate. Sketch that if you don't know. Or you probably, sketch this because you're not going to remember exactly all the details I need to here. So you've got a reaction. I'm going to scroll up some and I'll explain. You've got a reaction mechanism that has 2 steps in it. So it's literally going to take one set of reactants and make one set of products. And then use those products to make another set of products. And I'll draw some more stuff on there shortly. First year teaching this, I did not teach about I taught about 2-step mechanisms, but I didn't show a graph with it. And AP College Board is crazy about graphs and diagrams as of recent. They saw this and they're like, so I felt real bad. So I make sure that I really do a good job teaching this part now. Like I felt really bad the first year. But people got 5s and it was good. So the first step right here has a huge activation energy because going from reactants to this is the potential energy of the reactants up here to the potential energy of this transition state here, it's a huge jump. So comparatively right now, you should see that step 1 versus step 2. Step 1 is going to be the slow step because it takes a lot of energy to get up to the activated or activated complex or transition state. So step 1 is going to be the slow step due to its very, very high activation energy. Step 1 forms reactants 1 and makes products 1. So that's representing the first elementary step we previously had on the page. Then products 1 are going to become reactants 2, so they're the reactants for the second elementary step. They have a little tiny activation energy that must be met, and then they come way down here to products 2. Okay, and knowing that information that we know, you can deduce that elementary step 1, also occurring slow means that its K value is slow, because K, the rate law constant, helps give you a little bit of information on the rate or the speed of the reaction. So you need to know these two things. High activation energy generally means a slow step. Slow step generally means low K. And then you would know if it's a slow step that this would be the rate determining step, and then you would look at the molecularity of the reactants to get the numbers you need for the rate law, the exponential from the rate law. I'll give you guys a second. Some of you guys are like artistes. It's for them because like your colored pencils and stuff.
Slow step has a little K value.
Because the K value determines the speed of the reaction, and if it's really slow step, then it's going to have a really low K. Okay, I can come back to this picture if needed. Okay, second example. This is a suggested mechanism down here for our above reaction. What are your 2 steps on determining if it's possible or not? All right, sum them up. Let's go through this fast. I'm not going to go real slow on these because some of these are quite easy. Okay, so what can cancel? So fluorine, this is a free radical fluorine, okay? That's it, okay? So we have NO, is that it? Yeah. NO2 sums here to be 2 NO2s, and then plus F2 yields 2 NO2Fs. Okay, does that match? Yes, okay. What's the second criteria? Okay, which is the slow step? The one so slow. Okay. Does the molecularity of the reactants match the exponents of the rate law? Yeah, 1, 1, 1, 1. So then you would say both criteria have been met because showing the summative overall reaction being the same, that's one kind of justification point. Your second justification point would be you writing out the molecularity of the reactants of the slow step matches the exponents, or you could say orders. That's what I generally like to see. That matches the orders given in the rate law of those reactants respectively. You can get into like very fancy details if you want to, but saying the word molecularity is important. So, is it a possible mechanism? Yes. Alrighty. Sounds pretty easy. You will see some of these on your test, so I think you'll like that. Okay. Label the catalyst and intermediate. Which ones are the catalyst? Okay, catalyst. And which ones are the intermediates? NO2. I think somebody showed this example on their redox. Talk about ozone? Did your group talk about ozone on the redox? No? Okay, never mind. So anyway, this is ozone. What's the overall VC then for this? Knowing that the catalysts are going to cancel because they're unused, they're not involved in the rate law at all, and the intermediates therefore are also canceling. What's our overall? Okay, so this is the destruction of ozone. Notice ozone is here. Did you guys know this was ozone? Please tell me yes. Okay, so that's ozone. This is a free radical oxygen that steals electrons from other neighboring oxygens. That was our free radical here. right? Okay. And then makes 2 oxygens. Well, yeah, making oxygen up in the ozone layer, yeah, that's fine and all, but what about the big hole in the ozone? You know, there's a lot of environmental examples that you will see with rates and mechanisms, because there's a lot of real-life mechanisms that we see consequences of in biology and in environmental science. So this is a good one to just generally know. There's a catalyst that's not listed here that's behind this that expedites the production of ozone free radical, CFCs, chlorofluorocarbons, and there's a chlorine molecule that generally gets broken down to chlorine like that, and it's a free radical, and it will do the same thing. But nitrogen monoxide, which is coming from your car exhaust, if you don't have a catalytic converter on there, is going to be one that's another catalyst that will speed up this reaction. So those are like multiple choice questions that are knowledge based that you might make exam. Environmental impact questions. Okay? That's the only reason I mention it. I do like science though, in all sciences. Okay, so here's another proposed mechanism. Write the rate law expected for this mechanism. What is the overall balance chemical equation? You guys do that real fast. Anybody who's there, somebody tell me this, what the rate law is.
Concentration of C or
To the first. How did you know that?
it's the first step.
Go for it in terms of AP language.
The molecularity of the first step has to match the exponent of the rate law.
Right, or the order of the rate law. Okay, cool. So this was the first step. It was labeled slow, therefore you take the reactant, you find the coefficient, you plug it in as an exponent. Cool. And then you can add that up and get the overall. What do you guys say to the question?
Is it always the first step? Because like all the examples we do in the first step is the slow step, so is it?
It's not always that way. There's something, we're going to do a fast equilibrium example in the next one. A lot of times the first step is the slow step, because once the reaction gets going, there's different amounts of energies and different intermediates.
It's like it's easier to get going.
Yeah. But sometimes there's going to be one where it's like small peak, big peak, small peak, so you're going to have that second step being the slowest step.
But it's still the first step for the rate law.
For the rate law?
Yeah.
It's still the slow step for the rate law. Okay, even if it's not the first step, it's wherever the slowest step is, you write that as your rate law.
Okay.
Okay, so you guys can do the overall for that. What was your intermediate? Alright, so the cation, anything else?
The C4 H2.
Okay, so the other cation, okay, any intermediate, I'm sorry, any catalyst? No, okay. Let's do, this next one I think is the fast equilibrium one. No. This one's the one I want. Okay, so this one's a little different because now you're selecting which of these two mechanisms, this mechanism or this mechanism, which one is true for the following rate law and reaction given. So based on your knowledge of the two criteria that have to be met, try those. Try to figure out which one is true or which one is possible. We don't actually know if it's true or not because intermediates are kind of like ghost. They're hard to find. That one. No. Is that one on your paper at all?
Oh,
Yeah.
yeah.
Okay, I was making sure I actually found it. Alright, so some of you guys are there. Some of you guys are bored. I'll try not to be bored. For the first one, what did you guys say? First mechanism. Possibly yay or nay? Yes, okay, because the overall BC, when you cancel things out, that's an N, I think. Was it N2?
Yeah.
Yeah, okay. That, it matches what the first original overall BC was, and your slow step equals the rate law given. What did you guys see for the second one? Tell me more. So what was wrong here? Alright, so this is not L, this is a T. That's a plus. Alright, so right here you said, okay, so the rate is equal to K into O2 and H2, go to the first power. What is the very first step here then? What does the double-headed arrow mean? It's reversible. So the two NOs are colliding, two nitrogen monoxides are colliding to create dinitrogen dioxide, but it's happening super, super, super fast. This very first step is called fast equilibrium, and it is the fastest step of this mechanism. That means it's almost instantaneous. It's like immediately when they collide, you've made N2O2. So N2O2, is it around for very long? No, because immediately after that, it's going to get consumed in this next step. Now, I don't know how long that step's going to take, but it's going to start reacting immediately. So it's almost like you're reacting two NOs with the H2. So if you assumed that the two NOs react with the H2, what would your rate law be? NO what? Squared, or just NO squared, right? NO squared, and then H2. Is that what you're looking for your rate law? Yeah. Okay, so technically, this is a viable mechanism. This could be possible. The reason why is because the fast equilibrium in the first step creates an instantaneous product, which is then consumed as due to its intermediate nature. Now, is it likely for 1, 2, 3 reactants to collide? Is it likely for a termomolecular to occur? No. That's why we do not write it as that, because termomoleculars are very rare. They generally don't align and orient themselves correctly. Therefore, if you write it as a termomolecular, it's less likely to be thought of as a possible probable mechanism. Because truly what happens is it doesn't collide as three things together. Truly what happens is those two NOs, nitrogen monoxides, collide really fast, makes the dinitrogen dioxide, and then that immediately collides with the hydrogen gas. So it truly is just a bimolecular reaction, but the first step happens so fast it's sometimes thought as that is replaced, and therefore is termomolecular. So I have this proof. So I put it on the bottom down here. I'm going to show you, well, yeah, I'm going to show you though in a second. I just need to work it out up here. So I'll show you and walk through it with you after I go through these last couple bits here. So this is something I pulled from your book. It's just a good summary slide of all the rates and how the molecularity and the elementary steps relate to each other. So termomolecular, rare, A to the third order. So the rate law, if it's this, assuming, what are we assuming though for all these elementary steps if we write the rate law for them? Right, we're assuming all these are the slow steps. You can see how they relate. You guys get the point here? Okay. So, and with this example, it's just another example of the high activation energy with the transition state. We talked about that way long time ago. I just haven't taken out some of these slides. This one, we're going to talk about catalysts really briefly at this point. With this one, you can see ozone reacting with the free radical, forming the two oxygen molecules at the end. How many steps does this say this has? How many elementary steps? Which one is the catalyzed pathway? The red one. So is the so for the catalyzed pathway, it has how many steps? 2. Boom, boom. Is the catalyst that we originally had written down there like 2 or 3 questions ago? One of the catalysts were nitrogen monoxide. Another example I used were CFCs. All right. So technically, the pollutants that we were putting in the air are catalyst for a bad reaction. We don't want the ozone declining like that, right? So if we don't put the pollutants in the air, we do have catalytic converters in our car, so there's no nitrogen monoxide being produced. We don't use CFCs. What can you say about the kinetics of the reaction? All right, so the higher activation energy of the normal reaction, uncatalyzed, high activation energy would yield a slow reaction, which would yield, well, that's what Daniel said, high activation energy yields a slow reaction. So this reaction is less likely to occur if we don't pollute the air. You see the point? You see that the environmental comes right back in. So you might have to be reading a lot about environmental, like pollutants and stuff like that, and then compare that to how that relates to life. APBio does it a lot, right? Okay, that's why. Yeah, APBio has a lot more life and implementation examples. We sometimes back away from life for a little while, but we have to jump back in every now and then. Okay, so here's the homogeneous and heterogeneous examples of catalysts that we briefly talked about. I just want to show you guys last kind of final touches here. So for a homogeneous catalyst, this is going to be generally, homo means same, so we've got all the same phase reactants in our example. So these are all spread apart from each other, therefore they are gases. Okay, so these are all gases because they're all spread apart from each other. Then at the other opposite side of things, we have the heterogeneous catalyst. We've got gas phase up top and then solid phase down here. What was an example of a solid phase metal that I said was a catalyst? Platinum, gold, and lead. So those are some examples that you will use. Which one's in the catalytic converter? Platinum. Sometimes, well, no. Lead is lead. Oh my gosh, good example. Sorry, I read about this. I can't remember when I read about this. Why is our gasoline unleaded? Because it poisons the platinum. It messes up platinum, which, because if we have lead in our gasoline, it's combusted and then carried out through the exhaust, and if there's lead kind of vaporized into that, it would mess up the platinum catalytic converter, which the catalytic converter is put in to protect the EPA regulation to protect the environment for the exhaust coming out of the combustion reaction. So we have to have unleaded gasoline because it would be counterproductive to have leaded gasoline, which destroys the catalytic converter. If we're going to have one, we have to have both, because if not, they both won't work. So that's why you have the unleaded on your gasoline. Fun fact, guys. Oh, okay.
I did too.
No. No, it's not. No, but okay. So another example of catalysts you already know are enzymes. Enough said. Specific shape though, they're weird. Last year on the exam they asked them about DNA. It wasn't like the fact there was a double helix. It said what holds the strands of DNA together. What bonds hold the strands of DNA together? Hydrogen bonds. Okay, it's hydrogen bonds. Hydrogen bonds in biology you say are weak, but hydrogen bonds in chemistry you say are strong. I don't like to always blend them because we emphasize different things in bio and then chemistry. But we are infusing more earth and bio into chemistry, so we have to make sure we know, one second, that enzymes have a specific shape. Know it. They fit with a specific substrate. It catalyzes a reaction. Yes, ma'am.
So during biochemistry, what would they teach you?
The truth about everything. No, it's just that chemists take on a slightly different perspective, like with bonds and molecules, than biologists do, because they're not concerned about the bonds really. They're concerned about what affects in the body. So like, I have to lie to people in biology. My little baby biology class, it's sad, because I know it's not true. It's just a different perspective. Okay, we talked about this already. Let me make sure that I already told you everything here, and then I'm gonna let you. Actually, you guys work on your 15-question mechanism problem set. It's 15. Work for about 15 minutes, and then I'll pick back up on notes. Let's do that. It says mechanism practice. Yeah. Yep. The first thing it looks like is there's a castle. Do you see the castle? Yes. Okay. It's the first thing you're looking at. Looks like a joke. I will find you a joke. I will work on that.
A good joke.
Did I tell you how to? Did I already tell you how to say silicon in Spanish?
Yes.
How? Okay. Oh.
Yes, I just said in English.
English. Great. 15 minutes. You got this. 13 questions. Yeah. I'm sorry. What's up? Oh yeah. Thank you.
I'm sorry.
I'm a favorite.
During me?
Yeah, like, I'm just so tired.
That's what I try to make it exciting. Sometimes I talk a lot.
I didn't last class.
We should all
too,
chip
so.
in for a coffee machine. I took a nap last class.
I don't like coffee. Like, really?
Can we
please? I would.
I have a coffee machine now. Put a coffee machine.
Sierra's really good at getting me off task. I'm looking at the notes to make sure when I tell you all this stuff, actually. You stay on task. But coffee is very distracting. Yes. Yeah. Problem set. You should get full credit because you should get the whole thing done right now.
I'll sing your song.
I'll give you some running music. Let's do that.
Okay. Eye of the tiger.
Running music. Whatever Pandora puts on is what we put on. I also have not taken attendance.
Sugar, chocolate chip cookies. Preheat your oven to 375 degrees. Melt a half a cup of butter and add in 3